Hi, and welcome to the first of about 3 lectures on Chapter 3. Now, Chapter 3 introduces the first law of thermodynamics, of which there are a total of 4, but they are numbered 0, 1, 2, and 3. So technically, this is the second law. Now, before we get to what it is and how it works, we actually need to discuss some terminology. The first thing I'd like to discuss is the difference between what's considered a system and what's considered an environment. So, if you think of, for example, let's pretend you're at the beach and you have some sort of igloo or something like that for your drinks. So, here it is right here. Now, inside your igloo, you have ice. So, it has a low temperature in here. Okay. Whoops. Ice. There. Now, on the outside, you have the beach, you have hot air. You basically have the rest of the universe. Okay? So, for the sake of our class, the igloo container and what's going on inside would be considered the system. But the system itself lives in the real world, it lives in the rest of the universe. This is called the environment. Now, that said, there is a boundary. We'll say it is the insulation of our igloo or whatever this is. That is the interface between the system and the environment. Okay? So, for all intents and purposes, as long as the lid stays closed, and this is a good one, a good insulator, then what you have in the inside is things that are in equilibrium, specifically thermal equilibrium. Okay. Now, it's true that energy can leave your system and enter the environment. And it's also true that energy can leave the environment and enter the system. Okay? So, we're going to discuss these particular cases. But generally, when we talk about a thermodynamic system, what we're doing is we're restraining the conditions such that we can take advantage of things on the inside either changing very slowly or not at all. Now, so that said, um, if you think about what goes on inside the cooler here, and let's think about this as being a gas, we say that the temperature on the inside, the volume on the inside, whatever pressure is there, maybe the amount of matter, the mass, the number of moles, the number of molecules, whatever. We know that if this were a gas, again, just as an example, that we could combine these things and come up with something called the ideal gas law, which one version, looks like this. Now, the critical thing here is that you have these variables that correspond to what's going on the inside from a thermodynamic standpoint. Okay. Now, I mentioned in the previous series of lectures that this is an example of something called a state equation. Pressure, volume, temperature, number of moles or molecules, typically mass, something like that. These all uniquely define the properties of the system at a given time or in a given state. So, one way that we can express this is to move this to the right hand side or this to the left hand side. I'll move this to the left hand side. PV minus nRT is equal to 0. And what you would do is you would call this function f. Now, f itself is your state equation. In this case, it's a function of pressure, it's a function of volume, it's a function of the number of moles, and it's a function of temperature. It's equal to 0. So this is a state equation. And state equations are useful to us because they uniquely identify the properties of your system in this particular configuration. For example, with an ideal gas, if your gas has this pressure, this volume, this number of moles, you know what its temperature is going to be, through this particular equation right here. So like I said, it uniquely identifies the state. Now, that said, the variables that operate within a thermodynamic system typically fall up under two categories. You have what are called extensive variables, and then you have intensive variables. So, extensive variables deal with things that change if you were to increase the size, the extent of your system. Let's pretend that I somehow mysteriously doubled the size of my cooler. So in doing so, I would mess around with the volume, and I would also mess around with the number of moles if I was trying to keep the same environment on the inside. I would have to increase by nature the amount of stuff that I have in there in order to preserve T and P. So because those things change by changing the scale or the size of our system, we say these things are extensive. So volume and number of moles, perhaps molecules, if you're using capital N, or even mass. Okay. Now, on the other hand, pressure and temperature are microscopic quantities. They're things that aren't affected by changing the volume of this thing, okay, or changing the size. So temperature and pressure, we say, are intensive. They're interior, if you want to sort of think of it like that. Now, now that we've gotten a little bit of our, I guess you could say, terminology out of the way, what I'd like to do now is to discuss the first law of thermodynamics. All right. Now, so let me remind you about the zeroth. The zeroth law defined what thermodynamic equilibrium is. So basically, it says that if you have, three objects, we'll say A, B, and C, and I tell you that object A and B have the same temperature, and I tell you that object B and C have the same temperature, we know that means A and C are both in thermal equilibrium. They both have the same temperature as well. Okay, so that's the zeroth law. Now, the first law is sort of like conservation of energy for thermodynamics. If you look at the way your book writes it, your book says that a change in internal energy is equal to Q minus W. Now, I'm going to change terminology here. To date, your book is the only one that I've ever seen that uses this particular syntax for internal energy. Typically, U is used for internal energy. So the way we would normally write this law from a differential standpoint, which is the most common way that you see this used, would be that du is equal to dq minus dw. Now let me define what these things are. This is the change in internal energy. Now, what do I mean by that? Well, you can change the temperature. When you change the temperature, you change the motions of the atoms and molecules inside something. And as a consequence, the energy on the inside changes. Or it could undergo a phase transition. Again, this is the energy in the actual individual atoms and molecules. dQ is heat added. Really, it's the change in heat. dW is work done on the environment. And what the first law of thermodynamics tells us about is where this energy is allocated when your gas or whatever it is goes from one state to another state. Now, so that's said. We typically call this a thermodynamic process. Okay, so a thermodynamic process is a change of states, and by state I don't mean a phase transition. I mean it could be a phase transition, but basically you're going from one combination of PV, N, and T to another combination of PV, N, and T. Okay, so for example, maybe you're increasing the pressure, but you're decreasing the volume. That's going to change your state. All right. Now, so there are some conventions that you need to be aware of when you work with this law. First of all, one of the most common ways that you see it written is dq is equal to du plus dw. Now, here, dq can be positive or it can be negative. The convention is that it's positive, and positive means that you are adding heat into the system. Okay. Now, the negative is that you're taking heat out. As written, it's considered to be positive. Now, likewise, dW can be positive or it can be negative. Now, to be clear, du can be positive or negative as well. But we know that that's going to correspond to changes in internal energy. dW, though, if it's positive, your system does work to the environment. And if it's negative, your system has work done on it. By the environment. Okay. Now, so, like I said, conventions as written, if you take and you will say add heat into your system, that heat has two places that it can go. It can go into changing the internal energy. By changing the internal energy, we're going to talk more about what that means in a moment. You could, increase the temperature, or you could add to a phase transition or begin a phase transition. It can also go into work. You could cause, for example, let's pretend you have a balloon and you cause it to expand. You add heat into it, you heat up there on the inside, it expands. Well, the act of expanding has the balloon pushing on the environment, which means that it can do work on it. We're going to see examples of that here in a little bit. Now, this is actually a very useful law right here. And I would like to point out something else. Sometimes in more, I'm going to air quote, correct notation, you see it written the following way, with little slashes through it. And the slashes mean that these are not exact differentials. Now, what do I mean by that? Well, if you remember way back when we were talking about chapter one of the things that we covered towards the end of that was, heat transport. You had conduction, you had convection, and you had radiation. Now, I'm just going to focus on radiation for the moment. I'd like to remind you that you had this law that was called the Stefan-Boltzmann law. And what it did was to tell you about the intensity of radiation, or I think it was actually power was the way it was written. And it was sigma epsilon A T to the fourth. Okay. And so power, remember, is energy over time. Now, the study of thermodynamics is the study of temperature and heat. So what that means is that if you have something that has a temperature, if it has a temperature here, it's going to radiate energy, which means that even though your system might be, sort of isolated like this in an igloo, there is energy being lost in the environment that you can't really do anything about. And what that means is that our differentials here aren't exact because you have this potential for loss. Now, where that loss is and how we handle it is dealt with by the second and the third laws of thermodynamics. Okay? Specifically, the second law of thermodynamics. So just, maybe put a star, beside this in your notes and remind yourself that, in all probability, taken on a regular time scale, your system is going to be losing energy to the environment. Now, that said, when we do thermodynamics on paper, and we take an easier approach like what we're doing right here, a lot of times what we do is we sort of hand wave away any potential loss, and we do that by saying that we're we're changing the system very slowly and gradually, such that we aren't actively affecting the equilibrium that's on the inside. Okay. Now, so what I'd like to do is to just show you some very simple examples as to how this works. So here you have 300 joules of heat that goes into heating a pot of water. If no work is done by or to the pot of water by the environment, what changes in internal energy does the water experience? Well, so what we're given here is that 300 joules of heat is being added into the pot, which means that our dQ here, which is the heat that's being added into the system, which is our pot, is positive and is 300 joules. We're also told that no work is being done. dW is equal to 0. What we're trying to find here is du, the change in internal energy. So what you do is you write down your first law of thermodynamics, like this. Note the fact that this is 0. And what this says is that any heat that I apply is going to go strictly into changing the internal energy. So what's the change in internal energy? It's equal to dQ, which is just 300 joules. So pretty easy. Now here's another example of an easy one. We have 500 joules of heat that's being applied to a balloon. The balloon itself is going to experience a change in internal energy of positive 200 joules. That means its temperature is going up. Now, what I want to know is how much work is being done by the balloon on the environment. So what I'm given here is that my heat, dQ, is positive because my system is being heated. My balloon's being heated. So it's 500 joules. du is positive as well. And I'm trying to find dw. So dq is equal to du plus dw. And in this case, dw is just equal to dq minus du. dq is 500 joules. du is 200 joules. The difference between the two is 300. So how much work is being done? 300 joules. Okay? Now, so that said, let me add a few more pages here. That said, what I'd like to do now is to examine the first law of thermodynamics. But what I'd like to do is to consider some very specific cases. Now, I want to be clear, all of what I'm doing right now deals with the ideal gas law. So when I get to video 2, I'm going to talk about what happens whenever you have to deal with a non-ideal gas, for example, through the van der Waals equation. So let me write down the first law of thermodynamics again, which says dq is equal to du plus dw. And what I'd like to do is to focus specifically on dw itself. Okay? Now, dw we've seen before. We saw that back in University Physics 1. And if you remember the way it was written, it was F vector dot dr vector. Now, what I'd like to do is to consider a situation where you have a piston. So let's pretend that this is some sort of cylinder. I'm actually going to take and clean the end off here just to make my life easy so you can see what's going on here. Okay. And excuse me. And so here's the piston itself right here. And then maybe there's some sort of plunger here on the end like this. And, I don't know, maybe this plunger, I'm going to freehand this. Maybe this plunger is pushed up against a roller skate. So here's some wheels. Let's look at a roller skate like this. Now, so if I look at the state of, we'll say the gas that's on the inside and the side here, this is a void right here. It has a volume. I'm going to call V naught. Actually, I'm just going to call it V. It has a temperature, and it has a pressure, and it has a number of moles. Now, what I'm going to do is I'm going to add heat in. And as a consequence, what's going to happen is the gas molecules on the inside around, they're going to bounce harder and harder and harder. And many of them are going to bounce on this side of the piston right here. And what they're going to do is they're going to exert a force this way over the area of the piston. Now, what they're going to do there is to cause this plunger to slide this way, a distance that I'm going to call dx. Okay, so what we have here is a force that's being applied along dx. So that's work. Okay, now forces we know are nice to talk about, but a better way of dealing with forces is how they're applied over an area, and that's pressure. So if you think about it, we know from our conversation back in University Physics 1 that pressure is just force over area. So I can rewrite my force here as just pressure times area, which means that my work, which originally looked like this, now looks like pressure times area times dx. Now let's take a look at A times dx. Now this thing is going to slide from here to here. So it slides over a distance of dx. A does not change. What you're looking at right here is a change in volume. Your change in volume is the area times the change in displacement along this way. That's what accommodates the change in volume. So this right here is dV. So from a thermodynamic standpoint, we typically write dW as P times dV. Like that. Now, excuse me. So, dQ is du plus P times dV. Now, I'm going to disregard this for the moment. And what I want to do is to consider a couple situations in which work may or may not be done. Now, these are pretty common thermodynamic situations, so we're going to name them here, and you're going to want to make sure, again, that you put a big star in them or beside them in your notes, because these are actually a pretty big deal. So what kind of change do you typically see in a system as it transitions from one state to another state? Well, that transition could occur at a constant temperature. So, for example, maybe you increase the volume of a gas by increasing the pressure, but you do it slowly so that the act of increasing it doesn't cause the temperature to go up. That means that you've maintained your temperature constant. We call that isothermal. Constant temperature. Now, another way you could potentially change the state of your gas would be to hold the volume fixed and let all the other things change. So, a situation like that you would say is isovolumetric. Constant volume. Another way you could do things would be to hold the pressure constant. So with a constant pressure, you are isobaric, constant pressure. Now, there is a fourth one. There's actually another one as well that we'll talk about in the next chapter. But there is a fourth one called adiabatic. And that means constant heat. This would be a situation in which dq is equal to 0. Now, in many cases, this is what we're really wanting to take a look at. Situations in which there is, at least over a very short interval of time, no energy in and no energy out. Okay? Now, we'll be talking about this in a future video. What I'd like to do now, though, is to take a look at this equation right here, like I said, specifically the work part. And I want to see what it looks like for cases in which you have a constant temperature, a constant volume, or a constant pressure. The adiabatic one we're going to come to later on. So, what if you have a situation where, well, I don't know. I'll tell you what, let's start isovolumetrically to begin with. So isovolumetric means constant volume. So if I look at my work equation here, which is P times dV, and I ask myself, how much work is done by a gas expanding, or by a thermodynamic system expanding into its environment? Well, The hint here is that it's isovolumetric. So V is constant, and if V is constant, dV is going to be 0, which means in an isovolumetric case, your system is not doing work on the environment, and no work is being done by the environment on it. The volume itself is constant. Okay. Now, an easier case to begin with, other than the isovolumetric one, would be the isobaric one. So, in an isobaric situation, you have a constant pressure. Now, if I look at my work equation again, P times dV, P is constant, it doesn't change, which means that the only variable that I have on the right-hand side is the volume. So if I ask the question, how much work is being done taking this thing from one volume to another volume, if I integrate both sides? The P comes out, and this ends up being V evaluated from V1 to V2, whatever my volume is at the beginning to whatever it is at the end. And that's just P times the change in volume. Okay? So in an isobaric situation, the total work that's done taking a gas from point A to point B, or the work done by a gas from point A to point B, is just P times delta V. So that's pretty easy to deal with. Now, a more complicated situation is what happens when you have an isothermal one. So with an isothermal one, if you look at your work, it's still P times dV, but both P and V are variables. Now, thankfully, we have the ideal gas law that we can fall back onto to put this into a more convenient form. So remember, this is isothermal. Iso, not isto. Isothermal. And in an isothermal situation, you have a constant T. So here, PV is equal to nRT. And what I'm going to do is to take and solve this for P and plug that into here. So if I put that in here, this is now nRT over V dV. So if I integrate this, if I integrate the work from volume A to volume B, on the left-hand side, you have the total work. On the right-hand side, N, R, and T are all constants because, again, we're dealing with an isothermal situation. So N, R, and T come out, and now what you're integrating is dV over V from VA to VB. Now, when you do this, this ends up being a natural log. And if you take and you plug in the limits over here, and you use the law of addition and subtraction for natural logs, now you have an expression for the work done by an isobaric gas. So those are 3 of the 4 situations that we're going to be looking at. And I'm going to take and use these along with the first law of thermodynamics to examine a number of cases in the next video.